what actually it'll be what impurities there are.
All right, folks, let's do some simple combination circuits, then we'll do some that are slightly more complicated. Likely on this next test, you'll have both a multi-loop circuit and then sort of a combination circuit like this, where you have a combination of series and parallel. We'll get to multi-loop circuits maybe today or maybe on Wednesday. All right, but this one, most of you, if you're in lab, you've probably already done this circuit. It's pretty straightforward, and it's fairly simple. Probably not as simple as what you would see, or excuse me, more simple than what you would see in the exam, but we'll do some more complicated ones. So I have these three resistors. One is in series with resistors 2 and 3. And first thing I want to do is just find the equivalent resistance, like we did with the capacitors. And so here, for example, which two resistors would we start with? Right, the two in parallel. Y'all done this in lab? Y'all done resistors in series and parallel? Yep. Okay. All right, well, you find these two first. And notice they're common numbers that we've been using, so that's 1 over 1 over 3 plus 1 over 6, which you should know is what? 2. All right, that's equal to 2. And then I draw this circuit. I have R1, and then I have what I'll call R23. R1 equals 1, R23 equals 2, and I have 12 volts. And then I can find the equivalent of that, which is just going to be 1 plus 2 is equal to 3. So my equivalent resistance here is just 3 ohms. I'm at 12 volts. Now I can find the current that's going through this circuit. And what I'm trying to get at here is I want to know what is V and I for all three of the resistors. So I'll give you like a table, for example. And I want to know V and I for resistor 1, 2, and 3. So I can find this current here is just going to be V over the equivalent resistance. That's going to be 12 over 3 or 4 amps. Which of these currents is equal to 4 amps? R1, right. So R1 carries 4 amps. And then similarly, we can see that R1 also has a voltage, since I now know its resistance and its current. So I can say that V1 is I1 R1, and that's going to be 4 volts. That's 4 amps times 1 ohm, which is 4 volts. So I have 4 volts here. All right, so now things start to fall into place. What is my voltage across the equivalent resistance 2, 3? It's going to be 8. I can get that in two different ways. One, I can say that, well, the voltage here is 4 volts, so this has to be 8 volts because it adds up to equal 12. Or you can say that I have 4 amps in each of these resistors flowing across each of these resistors. And so I have 4 times 1, 4 volts on the first one, 4 times 2, 8 volts on the second one. With me? All right, so, and now I know if I have 8 volts, because resistors in parallel have the same what? They have the same voltage. I have 8 volts here, and I have 8 volts here. So now we're basically done. V2 is 8 volts, V3 is 8 volts, and then we can find the currents, which are going to be V over R. It's going to be 8 over 3 amps for R2, and then 8 over 6, which is 4 over 3 amps for R3. Don't worry, we're going to do some more like this. I know this is kind of fast, but we can do a check here by the junction rule. I know that a current coming through this resistor splits into 2 pieces, and the sum of those 2 pieces has to equal the current. This was what we called the junction rule, if you recall. The junction rule said that I equals I out. In this case, at this junction up here, at this point right here, our IN is which of the currents? Which current is going into that junction? 4 amps, right. I'm going to call it I1, right. And then that's going to equal the outgoing current, which current are currents? Right, I2 and I3. So I1 should equal I2 plus I3. So we have those values. We can just check our answers. So that should be 4 amps. Should be equal to 8/3 amps plus 4/3 amps. 8/3 plus 4/3 is 12/3. That's equal to 4, so that's a check. It's just a nice way to check your answers, that you can run through your circuit and check your junctions and make sure that your incoming equals your outgoing currents. All right, let's try another one. I think I have another one here. Okay, let's try this next one. First, find the equivalent resistance. Can I go down from here? All right, I'll give you just a sec. On that next one, take a few minutes head start, find the equivalent, and then I want to know what is the voltage and current in each resistor. Now to find the equivalent, which resistors are you going to start with? R3 and 4, right? Okay. You're welcome. Let's give this a voltage. Let's give it . Let's give this voltage 10 volts. Should make your answers pretty easy. Go ahead and find the equivalent resistance. I find it helps to draw out my circuits as I go along, but you may or may not choose to do that. Does anybody have the equivalent yet? Right, it's 5 ohms. So let me pull this back up. I have a series of resistances or resistors that are equivalent here to this circuit. So here I've just replaced those two R1, R3, and R4. What is this resistor that's unnamed right here? This one? What's that resistance? That's 3, right? So it's just 1 plus 2 is 3 ohms. And then I find the equivalent of this parallel branch. What is it? Right, it's going to be 1 ohm. Let me show you. That's 1 over 6 plus 1 over 3 plus 1 over 2. That's going to be 1 over 6 over 6. 1 6 plus 2 6 plus 3 6 is 6 over 6. That's just 1. And then I can find this resistor, which is 4 plus 1 is 5 ohms. Right. Now I can start filling in some things. What is this current right here? Right, that's 10 over 5, which is equal to 2 amps. Right. That gives me a current that I can start filling in. What's the first current I can fill in? Right, R1 has to be 2 amps. Because I know that I have 2 amps coming up off of that battery, and that's going to be the current that goes through that first resistor, because there are no breaks in the circuit. Likewise, that will give me my voltage, which is going to be 4 times 2, or 8 volts. Alright, now I can immediately start filling in some other values. What is V2 equal to?
2 volts.
It has to be 2 volts. The reason we know this is because I have 8 volts here. Let me go down to these equivalent. So I have 8 volts here. So that means I have to have 2 volts here, because 8 plus 2 equals 10. Or you could say I have 2 amps here. That's what I found right here. 2 times 4 equals 8. 2 times 1 equals 2. Either way you want to do that is fine. Right? So if I have 2 volts there, that means I have 2 volts here, 2 volts here, and 2 volts here. You can fill in some other voltages there. What's the other voltage I can fill in right away?
5.
Right, R5 is going to be the same. That's 2 volts, and then we also said R2 is 2 volts. Oh, I'm sorry, yes. So that's in my little table. What was that, 2 and 5, 2 volts and 2 volts. You can likewise find the currents there. Gosh, what are they? It's V over R, so it's what? 1/3 amp, yeah, 2 over 6, which is 1/3 amp for R2. What is it for 5? 1 amp. Now, that can tell us right away what is the current through R3 and R4. It has to be 2/3, right, because I know that I have a total, we're doing the junction rule here, I know I have a total of 2 amps coming in here. That current has to equal the currents that leave. I already know that I have 1/3 amp here. I have 1 amp here. That gives me a total of 1 1/3 amps. So I have to have 2/3 amps here and here. That's the easiest way to arrive at that answer. Let me show you another way you can do that. You can also say I have 2 volts across this branch, because resistors in parallel have the same voltage. And so I can say that I is V over R. That's 2 over 3 amps, which is what we get from the junction rule. So either way you can do that. It's a little easier going by the junction rule, I think, but you might choose otherwise. And then it's just a matter of using Ohm's law. So V is IR. For V3, that's going to be 2/3 times 1, or 2/3 volts. And without doing the same application of Ohm's law, what do I know should be the voltage for V4? This is by the loop rule, huh? 1 1/3, right? Because 2/3, if I have 2/3 volts here, I know the voltage here has to add up with this number to equal 2, because my total voltage across these two resistors was 2, so I have 1 1/3, just 4/3 volts there. Right. Or you could say it by Ohm's law, V is IR. I times R gives us 4/3, or 1 1/3. Very similar to the capacitor problems we had before, but your rules are all just a little bit different. So you have to make sure that you're applying the correct rules, and then there are lots of internal checks that you can do to make sure that you've gotten the answers correct. Alrighty? You'll see a problem like this on the test. Might even throw in another resistor or two. But there will be simple numbers like this too, or simple fractions maybe, but simple numbers. That's a good start to a Monday morning? Yeah.
Sure.
Yeah, all right. Okay, let's see. I think I have a few more questions that you can try on your own. Any questions about this? There's a lot of sort of thoughts that go into getting each of these answers, and you sort of have to take it in a linear sense where you start with that equivalent resistance. I find it very helpful to draw out your circuits. That way you can see what resistor is relative to all the other resistors. And then you sort of step backwards and you ask yourself, all right, well, what can I determine now? What is it that, you first find that first current, and then it sort of goes backwards from there. All right? As you get better with it, you might just be able to look at this circuit and just sort of see, like in the Matrix, right? What do you do? It's like you became the circuit. And then you can become the circuit, and then it's just, they all start popping up the answers. Okay, let's try this one. So, expect something along this difficulty. We'll see some multi-loop circuits as well, which we'll get to soon. First, what is the equivalent resistance of this circuit? If you finish this one, you can go on to the next. I think there are 3 questions, actually. Yeah, there are 4 total. Yeah, the next.
Really? We're going to do that? Right after the 4th question?
Uh-huh.
How fun. We're going to figure out how much power did it take to shut down to cause an entire blackout.
Right. Still on this first question, but if you finish this one, go on to the next, and the next, and the next. Right. Mm-hmm. Nice. About 10 more seconds. 2:25. I'll stop. 2:25. Somebody always waits till the very end. Click end. All right, 1. I think that's right. Let's see. Yeah, that is correct. So the first thing you want to do is find the equivalent of this branch. That's 1 over 1 over 2 plus 1 over 2. That's equal to 1. So I can replace this with a 1 ohm resistor. And then I have 2 series branches. I have this one, which is going to be 1 plus 1 equals 2. And then I have this branch, which is also going to be 1 plus 1 equal 2. And then I have, just two parallel resistors, 2 and 2. I've already done that right here, so you know what that answer is. It should be 1. 1 over a half plus a half is 1. All right. Given that, you should be able to look at this and just see what is the voltage and the current across each of these. Like, for example, I know the voltage across this resistor should be what? It's going to be 6 volts. Because both of these share 12 volts. So I have 6 volts and 6 volts there. What will be the voltage across this resistor? It's also going to be 6 volts because it shares 6 volts with this 1 ohm resistor that's right here. What then is the voltage across this resistor? What's it, John Marie? No, not 3. Resistors in parallel have the same what? They have the same voltage, yeah. So it doesn't split that voltage, but instead it shares it. This branch all together has 6 volts, and each resistor within it, because they're in parallel, also has 6 volts. So every resistor has 6 volts. All right? Did that answer the... oh, I'm sorry. That did answer this question. Right.
Now it's just memory. You remember what I said 5 minutes ago.
Right.
5 seconds.
5 seconds ago. I think the answer is A. I'm not sure.
You could do
Oh,
it,
yeah. Fix it.
You could do what Dr. Baker did. He did something really mean. He started coloring questions where he put one green and a couple of other ones red.
Uh-huh.
One of the real answer was one of the red ones.
Oh, yeah.
Thing.
Yeah, that's a good idea.
To jump on to one that you consider right.
But sometimes the green answer has to be the correct answer, right? Just to throw you off.
Yeah.
All right, just a few more seconds.
So much. Oh, thanks for a bunch of guinea pigs now.
Hey, good job. We can go home.
That was
All right, but remember that comes about because R3, well, we've already stepped through it, so I'm not going to step through it. Y'all follow this okay? Why these voltages are all the same? Hopefully you can just look at it and think about it in that way. So don't be overwhelmed when you see a bunch of resistors on a page because usually it's going to be a lot easier than it needs to be. By the way, did it help y'all or hinder you when I told you that the numbers for that capacitor problem were all whole numbers?
Didn't matter.
What's that? Oh, okay. I was afraid that it hindered you because it's like you think you got it right, but then you got 1.2 coulombs or whatever, and you're like, oh crap, I get it right. Okay. Okay, if R3 is removed from the circuit, what happens to the current through R1? If R3 is removed, what happens to the current through R1? All right, so a few more seconds. Let's stop at 50. C is right.
You sound surprised.
Well, C is...
I just guessed.
Let me show you. So, what you have to understand is that each of these are independent branches. So across this branch, I have 12 volts. And across this branch, I have 12 volts. They're independent of one another, but neither one of them knows that the other one exists. You can think of it that way. If I take one of them out completely, it's not going to affect the other. It's like in your house. If you turn off your toaster, it doesn't affect your radio or whatever. All right, so whatever I do in the bottom branch, even if I just took it away completely, it would have no bearing whatsoever on the top branch because they're independent, they're parallel, and they're independent of one another. So regardless of what changes I make in the bottom branch, it doesn't affect the other parts of the circuit. Well, let's ask another question. What if instead of removing, or let's say I remove R3, how does that affect the current R5 through R5? Let's try that one. So I remove R3 from the circuit. How does that affect the current R5? Same options, but now the current through R5. Do you all have the circuit in front of you? Looks like everybody does. You want to ask yourself what happens to the overall total equivalent resistance of that bottom branch, and that'll tell you what the answer is.
So what the top and the bottom is, would it split the current half by half from the top branch to the bottom branch?
They do split the current, and in this case it is half and half. But if you change the bottom branch, it doesn't change the current that goes to the top branch. It only changes the total current. So if you take out the bottom branch, the total current will go down, but the amount of current going through the top branch would remain the same. Follow what I mean? Yeah, so you get current to each branch, and that branch doesn't change. But if you change one of the branches, it changes the total current, but not the current in the other branches. Just a few more seconds. I'll stop at 150. Okay, look, we're sort of all over the board. So if I take out R5, if I take out R5, or excuse me, if I take out R3, what happens to the equivalent resistance? So first of all, I take this out. Initially, the equivalent resistance just of this branch was 1, but now the equivalent is what? 2. So if I remove a resistor in parallel, the equivalent goes up. So V equals IR. The equivalent resistance goes up, and now I want to know what happens to the current through this resistor. Let's try it again. I'll go back to your options. What happens to the current through R5? Get a little better histogram on this. Okay, I'll stop at 35. Couple more seconds. Okay, A is correct. If my equivalent resistance goes down, or excuse me, if my equivalent resistance goes up, then there's going to be less current flowing through that whole branch, the lower branch. All right, now let's look at this. Which resistor has the least current traveling through it? R1, R3, or R5, or they all have the same current?
That'd be really funny. You could maybe spam the button. It'll constantly send you put up the number.
What do you mean?
like if you keep on spanning, it won't. It'll just register your, but it like input the votes, kind of like you'd have your name, the answer be a million times, and then the number would keep on going over, and we all spam and see how high we keep getting it.
All right. Which has the least current? R1, R3, R5. Are they all the same?
I remember once for my biology class once, we had a class about 150 or something, and it started going into the 200s and 220, and we figured out that all the students outside are also sitting here, looking into the window.
You pick up other classes sometimes. All right, so a few more seconds, guys. All right, very good. B is the right answer. Look, we were picking up another class there because there was a D actually. All right, yeah. So I have the same I have the same current going here and here. I think it was what was it? We have 2 ohms, 6 amps. So I have 6 amps going here. I have 6 amps going here, and I have 6 amps going here. But here, that 6 amps splits into 3 and 3. So that current splits into 2 parts there. So R3 has the least current. All right. I think that was the end of those. Let's watch a little clip. You ever seen Christmas Vacation? National Lampoon's Christmas Vacation with what's that? Chevy Chase, yes. So this is a clip. Oh yeah, I'll get in trouble.